Yeah. So INCOSE India is a non-profitable organization and which has 18,000 plus members and which are still growing. There are 53 technical working groups and 74 chapters which are spread across 35 countries. And there are 3,701 certified professionals which are also affiliated with 120 uh, cab companies. So basically, INCOSE India, uh, we are registered as INCOSE India South Chapter in 2010, and currently we have 160 individual members, and there are 180 cab associate members. Uh, so INCOSE also provides certification, so out of which 61 are SCPs and 2 are ESEPs, 17 are ASEPs and 42 are CSEPs. And we are currently having 3 technical working groups, which are in architecture, MBAC and PHM. As I mentioned earlier, like INCOSE India chapter is active for last 10 years. So we have also get few awards which are in 2015 and 18 we got silver award, and 2019 first time we got gold award. And now recently in month of June we also got award of most improved performance in 1 year. So there are many activities which are getting conducted by INCOSE India chapter, uh, which are getting reflected into our awards. As I said earlier, we are now celebrating 10th anniversary of INCOSE India chapter, as well as INCOSE is celebrating 30th anniversary. Uh, so we just tried to have lot many things for this anniversary celebrations, but so webinar series is one of the thing what we are conducting, and hopefully when COVID is end, we'll be having a grand celebration in that way. Regarding today's webinar, so Dr. Ramakrishna is ESEPs, and he is also a principal system engineer at Honeywell. He is assistant director at INCOSE Asia Oceania, and uh, Mr. Ramakrishna is very much proficient in system engineering, and he has a great experience in system engineering. So we would like to know more about his experience and about today's topic, which is machine learning models for aiding system architecture and design decisions. Uh, so, Ramki, I'm passing control to you.
Um, Thank you, Kailash. So, hope you're all able to hear me. I'm just sharing my screen.
Yeah, able to see it.
Uh, so, hope you're able to see and hear me and see the presentation too. So good evening. Thank you for your interest in this topic. So first of all, I would like to thank the INCOSE India chapter and the leadership team there for giving me this opportunity to speak on machine learning models for aiding system architecture design decisions through. So as Kailash indicated, I am currently at Honeywell as a principal system engineer at Honeywell Aerospace. And I'm also involved with INCOSE since 2005. And currently I'm playing the role of assistant director at the INCOSE Asia Oceania sector. So we'll start off on the presentation. So the presentation outline is this. So we'll first talk about system architecture. We'll go into the context of what system architecture is all about through. And then we will start exploring machine learning models and how machine learning models can help in the system engineers to come up with good and robust architecture and design decisions through. And finally, we will spend some time looking at the benefits of using these machine learning models and the limitations through. So first we start off on the system architecture. So we'll talk about measures of effectiveness or MOEs. We look at the definition of system architecture. We look at what architecture decisions constitute, and we'll also see what the challenges for complex systems, right? So when we're architecting and designing complex systems, what is the challenge that we will face? And then we'll look at uncertainty. So this, the first part will give you a broad picture of system architecture and the challenges thereof. So let's begin by looking at the system lifecycle stages. So here you are able to see the typical lifecycle stages that are talked about while any system is being conceptualized, designed and developed and deployed through. So system design and development typically will involve the initial stages going from concept development, requirements, architecture design, implementation and integration test. And once the system is tested, it is then transitioned to production or deployment, and then it will get into operation and finally disposal through. So the last three stages is where the system will actually interact with the external environment, and the behavior and the functionality and how good it satisfies the requirements or the needs of the various stakeholders, becomes evident when it's actually deployed and used in the actual environment through. So a lot of organizations, the design development organizations are engaged in the initial part, going from concept development all the way to integration and test, right? And specifically system architecture design comes up here, where once we have some set of a baseline or a mature set of requirements, the system architecture and design activities start. That is the case for, say, a typical waterfall kind of model. But when you're trying to go for different other life cycle models, this picture will slightly vary. But essentially, a lot of critical architecture and design decisions decide how the system would finally function in its intended environment. So there are a lot of system lifecycle processes that are governing these activities. I think most of you may be familiar with the INCOSE System Engineering Handbook, the IEEE standards document. So a lot of these processes are outlined, the best practices are shared on how a team or an organization works through all of these lifecycle stages and builds and deploys successful systems. So a key concept for anyone engaged in the design and development of system is what is called the measures of effectiveness, or MOEs. So what are MOEs? MOEs are essentially the operational measures of success, and that's closely related to someone saying that, hey, that's a good system, or no, that's not a good system, right? So it is closely related to what is the objective of the system and whether it meets its objective, right? So any system is intended to meet its specific mission or operational objectives, and in the specific environment, right? So for instance, if you take a mobile phone, a standard mobile phone, it is intended to operate in normal temperature and things like that, right? So that's the intended operational environment. And then does it meet its functionality, right? Are you able to make a call, are you able to take a picture? All of those are its intended functionality. So are able to meet the intended functionality of the system. So that's where the MOEs come into picture, right? And typically MOEs are visible at the boundary of the system. So if you see the figure at the right side, you have a system A, and then it exhibits a set of MOEs, right? So they are the system A's MOEs, right? And each system is associated with what is the desired set of MOEs that it needs to meet. And in a sense, how do we say the system is successful or not? So here you can also see some examples. For example, response time to user action. So if you have a system which involves interaction with the user, so when the user interacts with the system and then he expects a timely response, right? So maybe in a 1 second response or a 2 second response, or at least some indication saying that, hey, I'm processing your request. It's going to take, maybe so much 5 minutes or 10 minutes to get back, or some progress bar. So those are some kind of MOEs for a system too. Similarly, time to alert, availability of the system. So these MOEs vary with each system, and these are critical to ensure that the system is successful. So what is system architecture? So if you see here, Basically, architecture, when you look at the definition, it talks about it's essentially the arrangement or the theme or the principles behind how the various subsystems. So you have a system and then you have subsystems under it. So how do the subsystems, what are the subsystems, how do the subsystems interact with each other, and how do they meet the overall functionality or the desired MOEs of the system, and what are the non-functional attributes or quality attributes, for example, reliability, maintainability, safety, etc. So what these attributes are and how well those attributes are met, right? So essentially there are two parts. One is on meeting the functional requirements, another is on meeting the quality attributes, or what we call as a non-functional requirements. So essentially architecture is all about in the solution space, what are the constituents of the systems, what are the subsystems, how do they talk to each other, how do they interact with each other, and all of these is done to meet the functional requirements and the non-functional attributes, right? So essentially we talk about architecture as a fundamental concepts or properties of systems. So on the right side, you see, like typically when you look at an architecture, there are different views like logical, dynamic, physical, or things like that through. So here you see maybe it's the logical view of the architecture where it says that, hey, there is a system, there are these 4 layers, there's a content delivery layer, there's an application logic layer, there's a presentation layer, and so on. And the next level details of architecture is typically called the design, the low level details. So here you're seeing an example of a software system. The design involves certain classes and certain functions and so on through. Right? And the quality and longevity of the system is largely determined by the architecture. So if the architectural decisions are not made optimal, or if the architecture is essentially it doesn't meet the requirements, so it's going to essentially not meet the MOEs of the system, and you cannot say that the system is successful, right? Or typically it's a failed system and so on. So essentially architecture is critical to ensure that the engineer system is successful. So architecture definition, you can see the standards like ISO, IEC, IEEE 15288. It talks about why does someone define the architecture, the purpose of architecture. It is to generate, hey, what are the different alternatives, right? Do I need to have, for instance, in this example, do I need to have a 3-layer or a 4-layer or a 2-layer or a single monolithic layer? Or which one is optimal for me, right? So, and which is optimal for meeting the requirements, meeting the functional requirements, as well as making sure that all the non-functional quality attributes of the system are met, right? And how good are the MOEs of the system met by the architecture. And typically there are different views that are talked about in the architecture, so we look at it quickly. The method framework also talks about architecture as comprising all the important decisions, right? So you can note that I have underlined the word decisions. We'll see, because that is one key part in which we will start building the machine learning models. So essentially architecture is nothing but making those decisions, right? And while you're making those decisions, what are the trade-offs? What are the assumptions that you're making, and what is the rationale on which you are choosing one option or one alternative or another, and how each of these choices are meeting the requirements of the system. That's on the architecture definition. So this slide talks about how to view architecture as nothing but a string of decisions. So on the right side, you see we have the architectural system, and essentially what it means that a set of decisions have been taken, right? A decision that, hey, we are going to have a presentation layer, we are going to have an application logic layer, there's going to be an XML interface. Now, how are these decisions made? Obviously, we would have one or more than one choice for choosing or for essentially meeting the requirements. So there are these set of architectural choices and options. And there are a lot of decision-making techniques that try to evaluate the different choices and options, right? And how does one come up with choices and options? It is based on the knowledge, right? The domain knowledge that is there. So there are all these architectural choices and options. For example, if you have to have a communication between one subsystem to another, should it be wired? Should it be wireless? Or what's the rate at which the data transfer has to happen? All of these are different choices and options that we have, right? And an architect has to make the right choices and options so that the requirements are met, the quality attributes of the system are met, and also the MOEs of the system are addressed optimally. Right? So the available choices and options need to be analyzed so that the MOEs of the system are met. and there are a lot of decision-making techniques. And typically, in a system that is multidisciplinary, so for instance, a system that involves mechanical engineers or mechanical engineering discipline, software engineering discipline, electronics engineering discipline, and all of these have to come together. A lot of these decision-making techniques will do what is called the multi-objective optimization. So these trade-offs would be crucial. For instance, what is optimal for software may not be optimal for the electronics. What is optimal for electronics may not be optimal for mechanical, and so on. So all of these trade-offs are involved in arriving at the various architecture decisions. But essentially, we can view architecture as nothing but a string of decisions that are to be made to meet the objectives of the system. So this model, so you can see a diagram here. If you're familiar with UML or SysML, or most of you might be, essentially it represents what is it that we're talking about the last few slides. So and anyway, walk through this notation. So here we say architecture is an abstraction of the system, right? So we have a system. A system has one or more functional requirements and quality attributes, meaning the requirements that it needs to meet. So that's where you have this 1:many relationship between the system and the functional requirements attributes. And each system also has one or more MOEs. That's the system MOEs through. An architecture is essentially an abstraction of the system. It abstracts the structure and behavior. Right? So in a system architecture comprises one or more architectural structures. So typically in literature, we talk about static structure, logical structure, dynamic structure, physical structure. For instance, physical structure will give a picture of the physical entities involved in the system. For instance, an enclosure, 2 or 3 cards, and then some come backplane bus that is connecting those cards. So all of those come under the physical aspects. The dynamic aspect typically is on the runtime interaction between the elements. For example, that's how it starts up, this is how it powers on, this is how it powers down, this is the continuous tests that are happening. So all of these interactions, right, when a user sends a command, these are the subsystems, and this is how each subsystem sends a message to the next subsystem, and so on. All of those runtime scenarios typically come under dynamic. Static and logical, typically the figures that we saw in the previous slides, they are typically come under logical or the static picture of the system. Right? So there are multiple architectural structures, multiple views, more to give a different perspectives of how the system architecture is abstracting the structure of the system. Right? And then we saw that the system architecture or architecting the system is essentially nothing but a string of decisions to be made. So system architecture essentially involves one or more system architecture design decisions. And each of the decisions are nothing but alternatives, right? So we saw the example, let's say it's a communication protocol. Then you have multiple alternatives like could it be wired, wireless, and so on. Right? And all the architecture decisions you are making, they would impact the MOEs of the system, right? So how good my system in the solution domain is meeting the desired requirements and the MOEs of the system is governed by the system architecture and design decisions. So this, in essence, this picture represents what we have been talking so far in terms of the system architecture, and system architecture design decisions, right? And the decisions you take impact the MOEs of the system. Now we'll move on to a key concept called complexity, right, or complex systems. So what is complexity, right? And typically in English, or the adjective complex is used to describe something that's difficult to understand, right? So complexity essentially means how difficult is it to accurately predict what is happening or to predict the future behavior of the system, right? So complexity is determined by the system being observed. So what is it I'm observing? The capabilities of the observer, that is how is my understanding of what the system is, and what am I trying to predict, right? So if you see here, the capabilities of the observer comes into picture, because say what is very complex for me may be very, very simple for you, right? So essentially it is I mean, it is dependent on the say the eyes of the beholder, right? Whether the system is complex or not. But essentially for a complex system, a lot of characteristics are talked about in terms of saying there are a lot of interrelationships, a lot of forces that are interacting with each other between the subsystems and so on, that it's very difficult to comprehend. But typically it's talked about that the human mind can comprehend about 7 ± 2 things at a time through. So when we have a lot of these relationships, complexities, starts manifesting. Like I'm not able to understand what is happening. I'm not able to understand what is going on. So there's a difficulty in establishing a cause and change. If I do this, what is going to happen? If I make this decision, what is going to happen to the system's MOEs? If I'm going to interact with a system like this, what is going to happen, right? It's very difficult to establish cause and effect chain. A lot of characteristics are talked about, so emergence, hierarchical organization, numerosity. So you can actually refer the literature. There's a lot of work that has happened on defining complex systems, the challenges of complex systems, and so on. Right? Emergent behavior, essentially, a lot of examples are given on the natural systems. For instance, a flock of birds flying in a formation. So when those birds fly in a specific formation, a specific emergent behavior comes about to play, right? Which is essentially the shape of the formation and the aerodynamics associated with the formation, and that cannot be attributed to any individual subsystem in that. Right? So that's with complex systems. So what are the challenges in the design of a complex system? So let's go back to look at the life cycle stages. So the period where most of the critical architectural design decisions made are here, right, in the concept, development, requirements, architecture, design. A lot of these decisions that you make has an impact of how the system is going to withstand the lab, the tests, how it's going to be deployed, and how it's going to be operated, utilized, and maintained, and so on, right? So a typical challenge that we face is, so we see the curve here. You can see it is up and then gradually coming down. So that is how easy it is for me to implement any decision, right, within constraints such as a budget and schedule. So for me, for instance, if I'm going to switch the communication protocol from a wire to wireless somewhere upfront, it is going to be much more easier than trying to do that switch downstream, right? So the ability to implement all of those changes within whatever cost and budget schedule that we have essentially reduces as the life cycle progresses through. But the challenge that we face is how much knowledge I have to make the right decision, right? When I'm going to say, okay, I'm going to make a wired versus a wireless, or I'm going to have it comprise of 3 subsystems as opposed to 4 subsystems, right? Now, that knowledge I have to decide whether it's optimal or not is obviously pretty much less in the upstream, and then it gradually increases some more, right? So typically when you start feeding the system in the lab environment or feeding it in the production or the actual deployment, there are a lot of lessons you learn in terms of, hey, we should have done it like this, or this is not optimal, we should have done something else. So all of this knowledge that we have essentially grows with the system, but the irony is all of these come pretty late, right? And all of the ability to implement any decision is more in the upstream, right? So this is a typical challenge that we face while the design of in the design of complex systems through, and a lot of life cycle models and all of that try to overcome this kind of challenge that we have through. So when you start looking at this, let's see how we can leverage some of the machine learning models to try and see whether it can help us in making some of these decisions better. So for complex systems, the key challenge that we face while making decisions is what is called uncertainty, right? So an architect, when he's trying to make a decision, he faces a lot of uncertainty in saying, hey, what is the implication of making this choice versus that choice? Can I choose this alternative versus another alternative? What is the bearing on the MOEs of the system? What is the bearing on the functionality of the system? Right? And the architect faces a lot of uncertainty in deducing the implications, right? And any wrong decision that he makes results in defects, rework loopbacks, undecided emergent behavior, and a lot of challenges, right? So a lot of complexities associated with making these architecture design decisions because there are a lot of decisions to be made. There are a lot of interdependencies between the decisions. A lot of knowledge areas. For instance, any decision may involve multiple disciplines, implications across multiple knowledge areas. Right? It may involve a software decision, may impact the electronics, it may impact the mechanical. So let's say I want to put a faster processor. It may impact that a lot of heat is generated, and it may impact the mechanical design in terms of heat sinks. So you see there's a lot of interdependencies between the decisions and a lot of diversity. And the key challenge is that whether it's difficult to get someone who is well versed with all the disciplines, right? Because practically it doesn't make sense to do a 4 years on a mechanical plus a 4 years on electronics and a plus a 4 years on a chemical or so on, right? So essentially that's why system engineers are called in, since they are expected to have the breadth of knowledge across multiple disciplines and the experience to pull together multiple disciplines and ensure that the optimal decisions are made from the systems point of view. And from therein, we are making the right decisions to meet the MOEs of the system. So significant interdependencies between and the multiple between the decisions and multiple implications of the decisions essentially is a key challenge that results in a lot of uncertainty for the system. So if you start looking at an organization, right, that is engaged in the design and development of system. So here I try to summarize what the challenges are. So essentially we have here three teams, right? Say a team X, team Y, and team Z. Team X is working on design and developing system A. Team Y is working on system B, and team Z is on system C. Again, this may be just on a snapshot in time. Many such systems would have got designed in the past, and many systems would be also in the pipeline in the future. So as you can see here, a lot of architectural design decisions made by different teams on the designing the various systems. So what are some of the scenarios that would the challenging scenarios that we will encounter in such an organization, right? So let's see one challenge. For instance, the knowledge gained on using a specific alternative is prone to loss, right? So for instance, there is a team that worked on designing system A maybe a few years back, and then they encountered a difficulty in a specific designation alternative. For instance, when they used a specific type of enclosure design to manage the heat or a heat sink there, right? They would have learned a lot of lessons, but then that the knowledge is prone to loss if it's not captured somewhere. And typically in an organization, different teams, the teams are just assembled to meet the requirements or to do the design of a specific system, and then they get disbanded once the system is designed and developed and deployed, and then we move on to different teams to do, right? So this is something that we often see in large organization. And there are these lot of chances for a lot of these lessons learned to be getting lost over a period of time, right? So that's one kind of challenge. Another kind of challenges the competency of the different architects. So in an organization you will see multiple architect designers of varied experience level, varied exposures, and there are a lot of these different architects and designers spread over the organization. And typically their bandwidth is also constrained, in the sense like very difficult to get the time of senior architects and designers. And so you will see a lot of novice designers, architects making these mistakes, and if only they get the time or the experience of the senior architects and designers getting transferred to them, you'll see a lot of these similar lessons being learned over different points in time. And similarly, we'll see that a lot of, if we start monitoring how good the decisions are being made, we'll see the fidelity varies across teams, or fidelity varies across, which kind of experienced people are there spread over. And then again, fidelity vary along different knowledge areas. For instance, we will see that probably mechanical discipline-oriented decisions typically have lesser rework as opposed to electronic decisions. I mean, we can start seeing some kind of trends and so on through. Some decisions may be more prone to rework. For example, the organization can see that hey, a lot of communication protocol related decisions are always hitting us pretty late in the system design development lifecycle, and so maybe that's an area of focus through and so on. Right? So a lot of such scenarios happen in a large organization that are engaged in the design and development of multiple systems over time. So that in essence, we have come to end of the first part, where essentially we talked about the system architecture, what it is, the fact that the MOEs of the systems need to be met. Then we saw complex systems and what are the challenges in developing and designing complex systems. And then we saw a couple of scenarios that would occur in an organization, right? Engage in the design and development of complex systems. So that gives us a good context for system architecture. So now let's start looking at machine learning models. So we'll start looking at what is machine learning, decision learning cycles, and how we can start leveraging some of these models to learn from the architecture design decisions being made, and then also start predicting or assisting the system architects and designers. So we'll move on to the second part. So machine learning, right? I know there's a lot of buzz about artificial intelligence, machine learning, and so on, and it's becoming more and more pervasive and essentially surrounding us through. And a lot of these is over the recent past. So we'll spend some time on looking at machine learning. So obviously, we'll not have a lot of time to go through a lot of basics of that, but essentially, there's tons of material available on in the web, and most of you might be familiar with it. But just to set the context, machine learning is essentially a set of computational methods that use experience and to improve the performance. So I saw an interesting analogy, on here. Like typically, when you look at a software program, we look at the program and it works on the data and it produces the output, right? But machine learning just does the different or the other part. You have the data, and then you have the output, and then you come up with a program that takes the data and gives the output, right? So essentially, machine learning is the field of study that allows computer programs to learn, without explicitly being programmed. So I think most of you might be familiar with, the standard example that's talked about. So let's say you give to a machine learning algorithm different images of cats and different images of dogs, then provided it's trained with a good amount of data with a lot of variations. Then you give it a new picture, and then it would correctly say that, hey, this is a cat or this is a dog. And most of us are familiar with this example through. So here you can see, as you can see, it's becoming more and more pervasive. So Siri, the autonomous driving cars, self-driving cars. You have the robots that are managing warehouses. You have Alexa. I mean, a lot of things where machine learning is making a lot of impact. And some of these techniques and algorithms, you see the one that's mostly used is the neural networks through, again, artificial neural networks. Actually, they have been around for a lot of decades, but then two things that actually brought this into prominence. One is the availability of a lot of data in the recent past, and another is the computational power that is available through, right? That lets complex neural networks through. So what are neural networks? Essentially, artificial neural networks are neural networks. They are a collection of interconnected units or nodes, and each node has a capability to receive an input or a set of inputs and do some processing and pass it on to the next node that is interconnected to it, right? So typically you see a structure of a neural network here. We talk about an input layer, essentially that has the inputs of the data, and then one or more hidden layers, and then an output layer. So for instance, if this is going to be a network that classifies images, then the images would be the inputs. Then you'll have a lot of layers here, and then you have the output that essentially says, "Hey, this is a cat or this is a dog." Again, there are two things talked about. The regular shallow neural networks and then deep learning. So in deep learning, essentially, you will see that a lot of feature engineering in terms of deciding what the features are essentially inputs that get in network. They are not worked upon. So the network itself learns what the characteristics of the important features that matter are. So that's how far we'll get into neural networks here in this talk. But essentially, we will talk about dimensional reduction as supervised learning, because that is what this work involves through. So we'll see about how do we employ these two techniques in the context of machine learning and neural networks to see how ML can aid system architecture design decisions. So essentially, the first part is that we need data. So going back to the figure that we saw a couple of slides earlier, we have architects who are making decisions, and these decisions, they have a lot of uncertainty while coming up with the architecture of a complex system. So first of all, we need the decision data, because we need data to train the ML model. So we need some means to capture the experience of the architecture design decisions as good or bad, right? So we need somewhere to label, just like we try to label an image as a cat or a dog. We need some means to label that, hey, this is a good decision or this is not a good decision or a bad decision. Right? So first we need to come up with that. Next, we need to arrive at some means to represent the decisions, right? Because essentially we need it in terms of electronics data, a software data element. So how do we characterize a decision, right? In terms of the decision attributes, right? We talked about decision essentially having multiple alternatives. So how do we characterize each alternative in terms of specific values of specific data attributes? So that's what comes as the decision. And then once we have that, maybe we'll be able to train some machine learning models and then use that for predicting and assessing the uncertainty. Right? So essentially the approach is some means to characterize a decision or label a decision as good or bad, some means to represent the decision, and then some means to use that decision data to train ML models and then start leveraging it. So we look at each of this in a step. So as the first part is, how do we say a decision is good or bad, right? So any decision we make, there's a point in time when we make the decision. And then after some point in time, right, maybe days or months or years, we realize that, hey, the decision is a good decision or a bad decision, right? So in this work, we try to characterize a decision in terms of four different stages. One is, yes, that it's a right decision, or it's okay, though suboptimal, but we can still live with it. Or no, we need to do some rework or patch up, what we call some surgery needed. Or no, we need to do a lot of rework, or we need to loop back to the point in time. Right? So for instance, let's say we decide that a specific communication protocol is to be used during the architecture stage. And then 6 months later, when we are doing in the lab, we find that the protocol is not optimal. Then that we need to do some patchwork around the protocol. Then probably it would be under the third category here. Right? We need some patch up. Or if you realize that yes, that's the right decision, right, with a good amount of certainty, then yes, it falls in the first category. Or let's say we have to go and do a total redesign back to the point in the architecture stage where we have to come and rework the whole communication protocol. Then we say that no, that's a bad decision. It was through. So essentially, some means to say that a decision are good or bad. So in this work, we have tried to say these four levels of saying that yes is a good decision or bad decision. And also the learning cycle days, right? How much time or how many days it took to realize that is a good decision or bad decision. So obviously, the shorter the learning cycle is, the better it is. So for instance, if I realize faster, right? If I make a design and I realize in the lab environment itself, then that is much better than realizing it once the system is deployed in the field, right? So shorter learning cycles are always better, right? So here is the integrated model we talk about. So I think we saw parts of it in a slide earlier in terms of the system architecture, system having MOEs and architecture design decisions impacting the MOEs. So now we try to expand it a little bit more. So any decision, it may be a mechanical or a chemical, it will involve mechanical engineering or chemical engineering or certain set of knowledge areas it will belong to. And then we try to capture the experience of the decision in terms of what is the learning cycle consequence. These are the consequence in terms of a good or a bad decision, the duration in terms of, it took so many days or it took a long duration or short duration, how complex system is. So you can take any complexity grade in terms of a low, medium, high, or any other what is followed in the organization. And then what are the unknowns or what are called the knowledge gaps. I mean, how to characterize a decision can be based on the organization's processes and how the system architecture and design is being practiced in the organization. So both the complexity knowledge gaps and the learning cycle model we'll talk about. It can be used to predict using ML models on what is the learning cycle that it would encounter. And then we'll talk about an uncertainty model to come up with the decision uncertainty. And then we'll use that to see how good the decision is for the system. So we'll see elements of that in the upcoming slides. The first learning cycle consequence. So here is a graph that you see. So on the y-axis is how the architecture or the design of the system is progressing. So from when the point in time an addition is made, my system progresses. At some point, the implication is realized, and if you realize that yes, it's good, that's LCC1. Yeah, it's optimal decision. If you have to do some, it can be lived with, though optimal, then that's LCC2 scenarios, which means yeah, it's okay to go ahead with that choice now. LCC3 is some minimal rework, so you actually see a dip in the progress of the system, some minor adjustment made. LCC4 is where you do a major rework. So that's where you see a major drop in the progress in the architecture design of the system, and then you have to catch up through, right? So essentially the different learning cycle consequences and what its impact is on the progress and the learning cycle duration is what this figure essentially talks about through. So there are two phases when we start looking at the machine learning model. So one is the learning phase, so where we try to codify the architecture design decisions, and then we build what's called the learning cycle model, and then prediction phase where we start using the model. Right? So what essentially we do here, and first we try to capture the decision data, represent the alternatives, and then have some means to represent the complexity of the system, and then capture what exactly happened for the past decisions. So once we do that, we try to analyze the learning cycle space. We'll talk about that. And then we use machine learning models to train based on the past decision learning experience. And then we formulate the uncertainty model. So we'll go through these 4 steps here. So how do we codify the decision experience? So here we see, this is an example. So let's say we have a decision that is to be taken on the operating system middleware, and then we have 2 alternatives or 2 choices, right? So we try to represent those attributes of the alternatives like scheduling, right? So while I'm designing the operating system middleware, do I adopt a cooperative scheduling or a rate monotonic scheduling? Do I adopt a periodic non-volatile memory writing or on demand? A lot of these choices and alternatives an architect is faced with. And so we try to represent each alternative as nothing but a set of attributes and set of values for this attribute. So for example, alternative 1 was used in this system, decision ID 1. Alternative 1 essentially means H1 was 1, which means a cooperative scheduling. And then it was on demand writing, and then 2, it used a ring buffer, and so on. Right? So if you look at this, essentially we have captured this decision knowledge saying in this decision ID used in a system with high complexity and where there were about 12 unknowns encountered a late rework, not a major rework, but then some minor surgery, and then it was in a moderate duration. Right? Actually, this is an example of how you can codify a decision experience. Obviously, this needs to be arrived at based on what is the life cycle processes, what is the architecture design process the organization follows through. So based on that, one would be able to arrive at what essentially makes sense. Right? But here you just see an example, and that this was the way the decision had. Um, Now, decision has multiple attributes as we saw earlier. So if you recollect, we said we'll do dimensionality reduction. So when a decision has multiple attributes, we can actually adopt a technique called the principal component analysis, or PCA. So when a decision has multiple attributes, like we saw 5, 6 attributes, it's very difficult to visualize that, right? So how do we reduce those 6-dimension or 8-dimension space into something that is more amenable and easier to analyze? So that's where a technique called PCA, or principal component access analysis, is used. So essentially, it sees here that of all the decisions made for communication protocol stack, it can be viewed as these 4 or 5 points on this single dimension scale. Right? So essentially, we are reducing those 5-dimensional communication protocol stack alternative or attribute to a single dimension, and try to do that. We'll see why we are doing that later. But essentially, this is a standard technique to reduce dimensionality of multi-dimensional decision space. Right? Otherwise, when you have these multiple decisions and each decisions having multiple attributes, we'll have essentially a 6-dimension or 8-dimension space. Right? Very difficult to visualize what's happening. Right? So that is where we see the benefit of using PCAs. So essentially, we'll see all the decisions taken for thermal design is probably at minus 1.5 or a minus 0.8 or minus 5 and so on. Once we do that, we have the learning cycle space. So essentially, we try to plot the various decisions taken on this 3-dimensional space, decisions, the system complexity, and the learning cycle consequence. Right? Essentially, we see multiple decisions. You can see here. You can see very interesting patterns that are happening. For instance, we can see a pattern that all decisions pertaining to enclosures, they are encountering a lot of rework here. Right? And they're also encountering moderate learning cycle duration, right? Before you know that the decision is optimal or not. So once we have this kind of learning cycle space and the data, so we have essentially decision data that talks about all the different decision experiences. Now we are in a position to feed into a ML model, a machine learning model here. So we'll not go into details, but essentially we'll see that by feeding this data, the ML model is essentially learning all the decision experiences that various architects and designers had in that organization, right? And it's able to able to predict that, hey, this is the learning cycle consequence or the learning cycle duration. Obviously involves a lot of math, probably will not go into that, but essentially in this study what we did was we just did use the shallow neural network for with 9 input layer units. So essentially 9 was for each of the attributes of the decision, right? In terms of the attributes 1, 2, 3, 4 and the system complexity knowledge gaps. And then there was a one hidden layer unit that was used through. So essentially, while you are doing any prediction, what is called the confusion matrix is then is kind of analyzed in terms of the performance of the neural network. So how good the prediction is. So in terms of if it was LCC1, did it actually predict as LCC1 or did it predict something else? Right? So the overall prediction rate, you can see it 96.9. Essentially, this is just a feasibility study that was done. So essentially, it says that, hey, there is a good potential for using machine learning models to capture the decision learning experience of the architects and designers. Obviously, we can come up with more sophisticated neural networks, deep learning, and depends also on the data that is gathered. And obviously, the network needs to be fine-tuned based on how the data turns out to be. But essentially, this establishes the feasibility, right? So how do you validate that? So we can validate it by again essentially saying that, hey, assume that we don't know this data, what the value to be predicted is, can we run this past again the model? So validation in terms of how good the network predicts the probability. So if we look at a specific row here, this says that LCC2 learning cycle consequence 2 was encountered. So essentially when you take these inputs and feed it into the network, and then it says that the probability on which LCC2 is encountered is the highest here, right? 0.97 on a 1 scale. So that essentially validates that the ML model has learned the decision-making experience in that. Right? So even when you think about the common example of classifying image as a cat or a dog, essentially the network would say what is the probability that it's a cat or it's a dog through, right? And it will give the highest probability to where it thinks the image is present. So similarly here, we are saying the network to what it thinks would be the experience of the designer. Okay? So once we have the learning cycle consequence prediction, we frame the uncertainty model. So this can be tailored and customized per the uncertainty or the risk-taking appetite of the organization. So here we see one specific model where we say that any decision where the learning cycle consequence is LCC1 and it's a short learning cycle duration, uncertainty is pretty low, right? And the highest uncertainty is given where you have to do a significant amount of late rework and you realize that it has to be done like that pretty late in the life cycle. Right? So once we have formulated such an uncertainty model, then we get into the prediction phase where we look at, let's say we're going to design a new system. What are the alternatives that we are considering, and then use a machine learning model to predict what's the learning cycle in the encounter, and then use the uncertainty model to come up with uncertainty, right? And typically, as you can see in this case, we have modeled the decision attribute in terms of the number of unknowns that is there, right? That was one of the data elements. So as the life cycle progresses, as the number of unknowns decrease, obviously it will impact the uncertainty or associated with the decision too, right? So you can actually have a monitoring mechanism in place to refresh the uncertainty assessments and feed that back to the learning cycle model, right? So here is an example that you see of potential learning cycle consequences predicted by the machine learning model. So as you start making new decisions, the uncertainty of various decisions are predicted in terms of for each of the decisions over a period of time, how the uncertainty varies. So what you can actually see here is that in some cases, as the time progresses, the uncertainty increases. Maybe that was because more unknowns got surfaced later. But normally it's expected the uncertainty decreases. In fact, you can actually have this uncertainty monitoring being tracked over periodically, and the uncertainty used to drive any corrective or preventive actions. So that we have seen as a brief of how the machine learning models can be used to capture the decision learning experience, and then aid the designer in terms of coming up with which decision is good or which decision is bad. Right? So we'll see quickly some benefits and limitations of this approach. So going back to the figure that we saw earlier, so now we had those three teams working on designing different systems. So now we have a ML model, machine learning model that essentially learns from the experiences of all these teams over a time, right? And then it embodies the decision-making experience through across the entire organization. So essentially, when someone is say one team is trying to adopt a specific alternative, then the ML model, if it predicts that, hey, based on past experiences of using that alternative in maybe in different teams in the organization in the past or something, the uncertainty of using that choice or alternative is pretty high through, right? Then the team can actually revise those decisions, or essentially say that, hey, that is needed, but we'll probably be cognizant of the fact that it's a risk and have some lot of contingency budget for that, right? Similar to how we are monitoring the decision uncertainty over a period of time, we can have those reviews and specific interventions on specific decisions that have high uncertainty, or where the machine learning model is saying that there's going to be a lot of uncertainty. And essentially, we talked about a scenario of varied competency levels of the architect. So essentially, ML model is now will be able to capture the combined experience of all the different architects over a period of time, through, right, and ensure that the knowledge is not lost. So some limitations, obviously, it's not a silver bullet, and a lot of limitations are there with machine learning models. So try to highlight some limitations here. Obviously, you need the decision-making experience, right, and a good means to codify it. Because how good you are able to feed in the data, that good ML model will be able to, go predict correctly and optimally the right decision. So one challenge is in case we are not able to have those data, then we'll have to start getting that data first within the organization, right? It can be through interviews or through specific sessions where we talk to experienced architects on their experiences in using various architectural alternatives and choices and what they encountered and so on. So we can capture those things and then start doing it. But then we can put some processes in place to ensure that in future or all the ongoing programs they have the experience captured. Similarly, how we model each experience, it has to be properly modeled in terms of the various attributes and things like that. So that codification is crucial. And then as new architecture design experiences are experienced in the organization, obviously the data have to be fed in back into the training for the new ML model to be upgraded and the latest experience to be available. So conclusions, yes, we saw an approach to leverage machine learning model, machine learning's approach to learn from the architecture design experiences and assess uncertainty, and also to enable the progressive maturity of the artificial knowledge base. Okay, so a question will obviously raise. So now we have the ML model or machine learning models to replace designers. Obviously not, but they can significantly augment the intelligence of system architects designers and essentially help in capturing the knowledge in the organization and try to give an advisory to the various system architects and designers to make the right choices through. So I think I've come to the end of the presentation. Probably I'll pause here for any questions or comments from the audience.
Thank you, Ramki, for sharing the information and giving us a good insight of making decisions and how machine learning approaches can be applied. Uh, so yeah, we have few questions. I'll try to uh, ask them one after another. Meanwhile, if anyone is having any questions, please ensure you are asking in everyone mode in chat window so that we're able to present it to the speaker. Yeah. So the first question is, can you suggest some good embedded platforms or PCB where we can host image-based machine learning solutions?
Uh, so the question is around the platforms on which we can host solution. So uh, I mean, it may not directly pertain to this, but yes, there are a lot of platforms you can talk about here. The boards through. So essentially, the trade-offs that you need to do to make the choice, right? It's in terms of whether the training, the learning happens on the fly or live. It's either on the edge on the device, or it's going to happen offline through, right? And then you feed in the train model. So that is going to impact your choice. So what I would suggest would be to list down the characteristics in terms of what the needs are, where the learning or the training has to happen, and where the fielding of the train model has to happen, because that will have a significant bearing on which is optimal and which is not optimal.
Okay. Uh, so the next question is, uh, how is the machine learning model validated?
Yeah, so in the specific case, we saw the validation in terms of rating for the past decisions, whether the uncertainty was right, or whether the learning cycle that was experienced, right, if it was uh, category 4 or category 3 or so on through. So that's how we validate it. And then as we use it for predicting how good the prediction was, and how what was actually experienced. So both these stages have to be used for validation. For the train model, the validation is based on the past history of what was captured and used to train it. So we don't give it the output and then we pass it to the ML model as though it is happening now, and then we try to see if it correctly predicted the learning cycle consequence.
Okay. Uh, so we have another questions. Do you have any consideration of similarity of the decision you use for training, and what type of decisions would the learned model be useful for? It seems you have some categorization of types of decisions, enclosures, thermal, etc.
Yeah, so the examples that you saw there were examples of decisions being made, say, in the region of a control system or things like that. Through. So when we try to look at a decision, how we have to characterize a decision, right? In terms of the attributes or the choices, and then what are the other information associated with the decision, the context information. Does it belong to an embedded system or it's an enterprise system? So all that information pertaining to the context of where the decision is to be made has to be part of the training set, right? In the example that we saw here, we just used in addition to the decision attributes, we used like complexity of the system, the knowledge gaps or unknowns in the system, and so on through. Obviously, for the specific system that is being designed or being worked on in the organization, we'll have to categorize in terms of the various types of systems and long cycle, short cycle, maybe the domain of the system. So all those attributes have to be used, and then using that, we'll have to see if actually the that is enough or adequate to predict correctly based on the past history, historical data. And if it's not there, that means we are missing something, right? So that is typically the approach when you go for shallow networks. When you go for deep networks, so probably we have to feed in whatever we think are the elements, data elements that might matter, and then see if the features can be figured out.
Yeah. So the next question is, do you build separate models for each type, or is the type encoded in the attributes or features?
Both ways. If using the type as an attribute, I mean, depends on the complexity of the decision data and the data that you have through, right? So if you want to build a separate model for embedded systems and a separate model for enterprise systems and so on through, right? That is a choice that you'll have to make based on the attribute of the decision. So for instance, if you're able to standardize saying that these 10 attributes of the decision can characterize an embedded system, it'll make a lot of sense to have a separate model for architecting and designing embedded systems as opposed to an enterprise system and so on.
Uh-huh. And now we have another questions. Uh, like, will not these decisions data used for training the supervised machine learning model vary significantly across domains? Example, what you extract from the decisions while designing an aircraft could be a quite different for the designing an underwater tunnel. And similar to the like there is another question similar to the aerospace. Uh, People want to know like an example on aerospace design, if any.
Yeah. So to answer that, yeah, obviously the domain matters through, right? Now, if you're able to get a good prediction by having domain as one of the attribute, right? So domain one, value one means it is aircraft or something else, and value two means something else or things like that. And if that is going to give you a good prediction, so ultimately it all depends on the data and how the ML model or the algorithm that you're using for prediction. Right? So as I indicated earlier too, if it's getting really complex or if you're getting good prediction, it would make sense. But then the benefit of cross discipline or cross domain knowledge transfer, right? That would obviously weigh in as a factor. Right? We're able to combine all of these varied domains into a single stuff and then single model, and then you are able to still achieve good prediction fidelity. You can actually go and see like, hey, this protocol was used in automotives, but it had these problems. Are we going to have a similar problem when we start using it in aerospace? Or this has been matured in automotive, but then probably it is still risky to take it for the aero space because the environment in which it operates is different through. So all of these needs to be factored in. So it all depends on how the database and how the algorithms work out through. Sorry, the data spread attributes that you use. But in essence, you have the option again to do domain specific models or an integrated model spanning domains through. But the key part is to capture the experience of the architects and designers to ensure that that is not missed and that is fed into the ML model.
Okay. So we have three more questions, but in interest of time, maybe we'll address one or two over here, uh, if they are quick to do. So what system architecture modeling language was used for your study?
So in this case, you can, I mean, SysML was used through. I mean, but essentially, when we start looking at the capturing the data, right? If you're looking at automation in terms of can we have some scripts to read through the model and then figure out what these decision attributes are? Yes, that is a open opportunity through in which we can explore automation. Uh, but otherwise, we'll have to dig through the documentation or things like that, the documents, and try to capture the attributes of these decisions. So modeling, I mean, models being made available or MBSE practices being used, it can facilitate easy capturing of the characteristics of those decisions. Definitely, that would help.
Okay. And this would be the final questions. So can you share some papers or tutorials which explain combining MBAC with AI or ML?
Um, Let me probably can contact me often. I'll have to search for that. Basically, looking at where AML is used in MBSE in terms of suggesting or aiding specific decisions. Sure. So I'll have to look through that and see. I don't recollect any offline through. Um, but before I forget, so here is where you will get more details of
Mhm.
this or this talk through. So this is actually a published paper, a digital learning framework for architecture of complex systems. So this paper actually covers both what we covered now for the system case in more detail as well as for the system of systems case through. So it's available in the system using journal that's published by INCOSE. So please do have a look at that to get more details on whatever we talked about now. So this work was done as part of my thesis work under the guidance of Professor Meenakshi of IIITB Bangalore through. So whatever we walked through here, I mean, we couldn't go into much details because of paucity of time, but you have the entire topic discussed in detail in this issue through. So please do feel free to refer that, and please do feel free to get back to me in case of any queries or comments.
Yeah, so people can always reach you through your LinkedIn profile, and your contacts are already listed there. And we have already tagged Ramki in our LinkedIn communication. So anyone who are having any further queries or want to get more guidance from him can always contact him through LinkedIn. Also, you can reach us at INCOSE, where we would like to know about any improvements you are expecting from us, or any further topics where you expect uh, speakers wants to share their thoughts and experiences. So we'd like to know about all these topics, and know about as well how the webinars are helping to you. With this, I would like to conclude today's webinar, and the recordings would be available on YouTube in COSE channel, and those will be available in another 1 week time. There are recordings already available on YouTube for earlier 9 webinars, so feel free to visit it and come with any suggestions or queries if you have. Uh, Thank you, Ramki, for sharing your thoughts, experience, and knowledge with everyone. And I hope it would be helpful to everyone. Uh, with this, I would like to thanks everyone and wish everyone a happy and safe weekend. Thank you.
Thank you all. Thank you all. Thank you.